All right, this video is going to take us through describing motion. All right, we're going to talk about all the different ways we can describe motion. We will get into how to describe motion through words, through word problems, through quantifying it, through graphing it. We're going to just talk about all the different ways that we can describe motion. All right, that's what we're going to be getting into in this next unit. All right, so motion, let's first define it. It says motion is relative. All right, well, let's figure out what motion is, man. Let's figure out what relative is. Motion is a change in an object's position when an object moves. Relative means in relation to something. All right, so it's going to depend on, like, so if you think of a relative, think of your relatives, family members you have a relationship with. All right, you have in relation to them, they're your relatives because you have some kind of a relationship with them. It's in relationship to you. All right, so we're going to try to understand this concept. It's kind of a goofy concept, but I'm going to give you a couple examples that hopefully we can clarify it. It says, if I'm in a car, all right, so motion depends on a frame of reference. All right, so a point of view. So if I'm in a car, I'm sitting next to my wife. I love my wife. She's beautiful. And I say, hey, babe, how you doing? And we just talk. Is she moving? Is she moving in the car? No. Well, she's not moving in the car. She's sitting right next to me. I can reach over at any point. I can touch her on the arm. I can say, hey, babe, we can hold hands. Well, she has not moved an inch. All right. So she has not moved. All right. So we're in the car. We're driving. My neighbor looks up, sees me and my wife driving by in our car. Are we moving? Yeah. Yeah. He sees us moving. We're changing position on the earth. All right. He sees us going from one area to another. We have changed position. You're like, well, that doesn't make sense. That's the exact same scenario. Me and my wife are in a car. One area we're not moving, one area we are. All right, how is this possible? How can the same situation have different answers? Because it all depends on the viewpoint. All right, because the frame of reference is different. All right, so from one perspective, no motion is occurring. From another perspective, motion is occurring. All right, so it's really going to be depending on how you look at it. All right, so we're going to dive into this a little more. So motion is relative examples. We're going to look more at this. If I'm in an elevator, I get in a hotel. I'm in a hotel. I get on it's at the 20th floor. I'm at the 20th floor of this hotel. I look down. I see a penny. It's tails up. Mama didn't raise no fool. I ain't picking that up. That's bad luck. So I hit the button to go to the lobby. I want to go to the lobby. The elevator goes down the lobby. Did the penny move? It depends, right? It depends on your reference frame. It depends on your frame of reference. How are you looking at the penny? Because if I hit the elevator door, I look down, that penny didn't get up and walk around the elevator. It stayed right there. All right? From the perspective of the elevator, the penny just sat right there. It just sat on the floor. There was no motion that occurred. All right? It didn't get up and do a little dance. It stayed right next to my foot the whole time. It did not move. But from the perspective of the building, the penny went from the 20th floor all the way to the lobby. All right, just like I did. In relation to the elevator, I didn't move. I hit the button and I stayed in that same spot in the elevator. But relative to the building, I clearly changed positions. I went from the 20th floor to the basement. So there's another example of how it depends on how you're viewing it. Did the object move? Yes. No. Maybe. It's how are you looking at it? From within the elevator, me and the penny didn't move. From outside the elevator, yeah, we did relative to the building. Here's another example. Train going by. Platform is the frame of reference. The tree is at rest. Well, if you're in the car or on the train and the train's moving, the tree looks like it's moving. It's moving in the opposite direction of you. You're moving this way. The tree looks like it's moving in the opposite direction. All right. And there is no motionless frame of reference. This says, do you think you're sitting still right now? You're on a planet that is orbiting a star at 30 kilometers per second. That star is orbiting the center of the galaxy at 250 kilometers per second. That galaxy is moving through the universe at a rate of 600 kilometers per second. Since you started reading this, you've traveled about 3,000 kilometers. Boom. Mind is blown. All right, so yeah, we're always in motion. There is no pure motionless frame of reference because our universe is expanding. All right. So motion is relative. All right, and then there's a couple ways we can describe motion with distance and displacement. These are two different things. All right, so distance is the total ground covered. All right, it's how far you travel. That should be pretty basic. We should have a pretty good understanding of what distance is. It's basically how far an object travels through its motion. Now, here's a new term. Here's a vocab term we're going to need to know. It's a scalar quantity. All right, that sounds scary. That sounds weird. Like, scalar, to have scales? I don't know what that means. Basically, in physics, what a scalar quantity is you only have to have a number with it. Right? You only have to have a magnitude. Just have a numeric value with it. There's nothing else required, no direction. All right. And it can never equal zero. If as long as motion occurs, you travel a specified distance. Now, displacement, that's another vocab term we're going to have. This is something you're probably not as familiar with. It's the total distance and direction an object travels from its initial position to its final position. Basically, it's the shortest distance between 2 points. So if I walk this path here, that's a long distance. The displacement is just that straight line. All right. It's how far I am from where I started to where I finished. All right, and in what direction. So this is my displacement because it's from where I start to where I finish. The distance would be significantly more because it's not a straight line. I walk that whole path. All right, and displacement, another vocab term you're going to know, is a vector quantity. All right, which means not only do you have to know the numeric value of it, but you also have to tag a direction with it. All right, so it has to have a numeric value. So if I say something is a vector quantity, all right, it has to have a direction and a numeric value attached. So you have to include the direction when you're talking about displacement. All right, it can equal zero because displacement, if I walked 10 steps, I go 10 steps this way, turn around and go 10 steps back. Well, guess what? I'm right in the exact same spot where I started. So my displacement is zero. All right. So it can even be negative if I were to walk past that. Because I walk past my point of origin. All right, we're going to do a lab with this where we explain that. All right, so displacement is relative. This is relative from where you start to where you finish. Distance is just it's the total ground covered. All right, get that out of there. I don't know how to clear it. Get out of there. There we go. All right, so it says my bike has a flat tire, so I walk to my friend's house. Point B. Mom tells me he's out of the tree. What is my distance I walked? All right, well, your distance you walked there, you walked 4 meters to the house and then 3 meters to the tree. You just add that up. It's pretty simple. Total ground covered. That's 7 meters. All right, but how far are you away from where you started to where you finished? All right, this is where I started. This is where I finished. I am 5 meters, so my distance would be 7 meters. My displacement would be 5 meters. And then since it has a direction, I put a little compass here. I'm going to be northeast of my initial location. So 5 meters northeast of my initial location. If I start at X and I walk following the arrows, all right, and I end at X, what is my distance? Well, 2 plus 4 is 6, plus 2 is 8, plus 4 is 12 meters. I walked a distance of 12 meters. What is my displacement? How far am I from where I started? I started at the X and I ended at the X. My displacement's 0. I'm right back where I started. Dog walks 12 meters east, then turns around and walks 16 meters west. All right, so he walks 12 meters east. Whoops. I don't know. I wanted to draw, but clearly don't have that as an option anymore. Walk 16 meters. What's the distance traveled? Well, 12 plus 16, you just add those up. All right, it's 28. All right, and then what is the displacement of the dog? Well, went 12 east, turned around, went 16 west. So how far are they from their initial location? So if the dog starts here, this is east, goes 12 east, and then turns around and goes 16 west. 16 west. How far are you from where you started? Well, 12. Now you're going to subtract these since they doubled back. 12 minus 16. I am 4 meters west of my location, of my initial location. All right, because I went 12 east, 16 west. I went 4 more meters west, or the dog went 4 more meters west. So it'd be 4 meters west. All right. Distance displacement here is just a graphic representing that. Nope, it's not. That one's not moving. That one should be moving. So this says, what is the distance and displacement of this person walking? Once again, if they start at A and they go to B, and then from B they go to C, they walked a total distance of 150 meters. But the displacement where they ended is 50 meters right of their location. Speed and velocity. Speed is the rate at which an object covers distance, aka how fast it's moving. That should be pretty common thing. The distance an object travels per unit of time. Speed is a scalar quantity. It's just a number. All right, once again, that's just a scalar quantity. Just need a number. The formula is the distance it's traveled divided by the time. All right, and typically your units, if you think about it, we say how fast you're going. I'm going 60 miles per hour. That means if I traveled, I'm going at a rate at which I would cover 60 miles every hour. All right, so it's a unit of distance divided by a unit of time. Velocity is a rate at which an object changes its position. It's a vector quantity. The number and the direction matter. Technically, if a person is moving forward and backward at a high rate, their velocity would be zero because they're technically not changing. There's no change in position. They ended up right where they started. All right. So velocity is actually a change in position over time, or basically another way to say that is it's the displacement of an object divided by time. We use these interchangeably, but they're really not. All right, because your velocity can technically be negative if it's moving in a negative direction, but you also have to have a direction attached to velocity. All right, so we use these two in our normal everyday life interchangeably, but in physics, velocity is a vector. It requires a direction, and it's really a change in your displacement over time. Speed is a change in your distance over time. All right, so those are the two differences. Here's how velocity, once again, it can be positive, it could be negative if you're going in the opposite direction. Once again, the number for speed and velocity should be the same, like in these scenarios here. All right, but one's going to be negative, one will be positive. All right, so speed you have to have, it's 25 meters per second north, or velocity, excuse me, and then the speed, you just need the number. And velocity of an object can be traveling at the same speed but different directions. They would have a different velocity. So it's traveling at the same speed, but the velocity is different because the object is constantly changing direction. Velocity depends on both the number and the direction. So if an object is driving in a circle, could be going at the same speed, but the velocity is changing because it is turning. All right, velocity 50 miles an hour north is different from 50 miles an hour south. All right, that value is different because it's obviously just changing directions. And then lastly, instantaneous speed. If I took a 5-mile trip to school, I had 4 different lights and a stop sign. Anytime I looked at my speedometer at any given point, it would tell me my instantaneous speed. So an instantaneous speed, that's another vocab term. It tells you how fast you're going at a particular instant in time. I look at my speedometer, I'm going 50 and a 35. Oops, my bad. All right, I got to slow that down. That tells me how fast I'm going at that moment. Whereas average speed, and this is typically how we're going to calculate stuff, is you take the total distance you traveled divided by how much time it took. All right. So if I drive 5 miles to work and it took me 12 minutes or 0.2 hours, what is my average speed to get to work? It would be 5 miles divided by 0.2 hours. My average trip, I get to work, I travel at about an average rate of 25 miles an hour. All right. So instantaneous speed, how fast you're going at that instant. Average speed is how fast you take over the whole duration of the trip. All right, and that's simply just calculated by taking the distance you travel divided by the time, how many miles you travel and how many hours it takes. All right, it's the distance traveled divided by time.